Industrial air compressors are built to take a beating, but over time, they degrade silently. To figure out exactly how much capacity an aging machine has lost, energy auditors use a primary diagnostic tool called the pump-up test. The concept here is completely physical. You close the discharge valve, start a stopwatch, and measure the exact time it takes the compressor to fill a receiver tank up to a specific target pressure. We translate that physical test into a raw capacity number using the baseline free air delivery, or FAD, formula. This maps directly to what we just watched. P1 and P2 are the initial and final tank pressures. PA is the atmospheric pressure of the room. V is the volume of our receiver tank, and T is the time on our stopwatch. Look at the two halves of the equation. The first part calculates how many times we multiplied the room's atmospheric pressure. The second part scales that multiplication by the volume filled per minute, giving us the compressor's true volumetric output. That baseline formula has a flaw. It assumes the compression is isothermal. In reality, when you squeeze air, it gets hot. That heat causes the air to expand, which artificially inflates our raw FAD number. To get an accurate reading, we have to apply a mandatory fix, the temperature correction factor. This is where exams trap you. First, you must convert your Celsius temperatures to Kelvin by adding 273. Second, T1 is always the suction temperature on top, and T2 is the receiver temperature on the bottom. If you skip this temperature correction, your calculated FAD will look much better than it actually is. That falsely high efficiency rating will invalidate the rest of your energy audit. Let's put this into practice. An industrial foundry suspects their aging compressor is failing to meet its rated capacity and orders an audit. This table summarizes the operating parameters recorded during the pump-up test, giving us the tank volume, pressure changes, time, and temperatures. Pause the video here. Use this data to calculate both the corrected FAD and the percentage capacity derating. First, we plug the pressure, volume, and time data into our baseline formula to get a raw FAD of 11.40 cubic meters per minute. Then we apply our temperature correction, adding 273 to both the 35-degree suction and 44-degree receiver temperatures to get a factor of 0.972. Multiplying those together gives us a true corrected FAD of 11.08 cubic meters per minute. The machine is rated for 14.25, leaving a capacity shortfall of 3.17. To find the derating percentage, you divide that shortfall by the original rated capacity, not the new delivery number. We need to know exactly how far the machine has fallen from its factory spec, which in this case is 22.24%. When capacity drops or air leaks spring up across the plant, the compressor spends more hours in its high-energy load state to keep up. This calculation block breaks down the hourly energy consumption based on loaded versus unloaded hours. Look at the math when we fix those system leaks. By dropping the load requirement from 70% down to 35%, the energy consumed per hour drops from 59.6 kilowatt hours to 42.8. The compressor still draws 26 kilowatts of power even when it's unloaded, but by minimizing those expensive, fully loaded hours, we secure the actual financial payback, saving over 400 kilowatt hours a day. Diagnosing capacity drops and sealing air leaks are direct interventions that slash the most expensive variable in your plant's energy equation. To master these compressor problems on exam day, you just need to organize 4 specific formulas. Start with your baseline FAD calculation, and then immediately apply the temperature correction factor. Remember to always convert to Kelvin. From there, calculate your percentage derating against the factory spec, and finally, map those run hours into the load and unload energy formula. Keep these 4 steps strictly sequential, double-check your absolute temperatures, and you have the blueprint to solve any compressor problem.